Welcome to Statistical Modeling Week 2. So today's lecture is about parameter interpretation in the linear model. So we will go through an example with data from Tech3 Lab and see how we can interpret the different models. So if you recall the basic model, we have a random variable y, which we express as a linear combination of p different explanatory variable x1 to xp, and there is an additional error term which we believe is mean zero, so our model is correctly specified on average. How to interpret the parameter in the general case? Well, beta naught is the intercept, so it's the value when all of the x's are zero, and again this may be meaningless, impossible, or it may be extrapolating beyond the range of the data. As for the other beta j's, for all the other explanatories, they represent the marginal effect of y, so it's the mean change of y when xj increases by 1 unit, everything else being held constant. And of course, again, this may or not be possible if you have two covariates that are a function of one another, or if you have interaction, if you have nonlinear functions. So basically, if an explanatory variable appears in multiple columns of x, you cannot probably fix x and increase by 1, and so the interpretation will change depending on the actual value you've observed in your sample. So this is the general framework. Let's look at a particular example, which is intention data. So in a study performed by the Tech3 Lab, subjects were asked to go on a website, and in one of the corners there was an advertisement for candies. And an eye tracker was recording the location of the eyes of the participants on the screen to see where they fixated. And they also recorded whether the subject looked at the advertisement and for how long. Afterwards, the people of Tech3 Lab use a facial expression analysis software called Face Reader to measure emotion about their perception of the advertisement and transform this into valence. And at the end of the study, there was a questionnaire to measure subject intention to buy and also some control variables such as age, education level, sex, and so on. So what were the objective of the study? Well, to see if there was a link between duration of fixation on an ad and their intention to buy, and see whether the perceived emotion is linked to the intention to buy. So you could feel in terms of user experience, if you're making an advertisement that has more positive emotion, probably it should be preferred. It might also increase the chance of the person buying the product. And so from a marketing perspective, this could be an interesting research project. So as for all the other examples in this class, the data are fake, but they do correspond to the study. And 120 participants we have in the database have seen the ad. So no one, all the people who screened the web page but did not look at the advertisement have been removed. So what's inside the database? What are the variables? So intention is actually discrete. And so it was created by combining two Likert scales. So two questions asked about the product, their intention to buy. And they were measured on a scale ranging from 1, which is strongly disagree, to 7, strongly agree. So if you sum the two items, the variable ranges between 2 and 14. Fixation is the total duration of fixation on the ad in seconds, and that's measured with some precision. And emotion is perhaps the hardest to grasp. So it's a measure of the reaction during fixation of the ad, and so the face reader software basically tried to estimate a probability that particular gram is showing positive emotion versus showing negative emotion, and then they take a ratio of those probabilities. So emotion score that's less than 1 means negative feedback, and the higher it is, the higher the probability. And if it's 1, the person is actually neutral. Okay, so emotion is positive. Then we have sex, which is encoded using a binary variable. So man is mapped to 0, woman to 1. We have the age and year, marital status, so single or in a relationship. And then two categorical variable ordinal. One is for annual income, so low income 0 to 20,000. Then 2 is a mid-range, a middle class 20 to 60K, and then 60K above. And likewise education, high school or lower, college, so CGEP and university degree. So these are our variable. Let's do a quick exploratory data analysis to see what are the range of values we can observe. And so let's start looking at this using this SAS, which we didn't really dwell on in the previous videos. So the first 3 lines in the code, starting with proc means, show how to extract a table of summary statistics. So here I've requested mean, standard deviation, minimum, maximum, and I've restricted the number of significant digits. So there's no point in having 8 digits for discrete variables, for example. And so this is the procedure means. I'm taking the data from the StatMod library, which you can access by either exporting the path to my particular folder in SAS on demand, or by creating your own StatMod library and putting the intention database there. So proc means, that's a call. Don't forget semicolon at the end of every line in SAS. Next, you specify the variables you want the summary statistics for. So here it's all of them: intention, sex, age, marital, fixation, emotion. And finally, we run the procedure. The second chunk of code is asking for a frequency table. So we know that some of those variables, including our response intention, are discrete or categorical. So it makes sense to see what are the counts. Sometimes specific models and trying to estimate effects for subcategories in which the counts are very few could be tricky, and so it's good to have a look and see how many people are there in each group and how is the data distributed. Okay, because they're categorical variable, of course, you could use a bar chart, but here we're going for tables. And the last thing you could do is plot a histogram of each variable. So it's going to probably provide you the same information as the summary statistics, or for example for intention, the frequency table, but it's probably easier to grasp. So this is the procedure SGplot that's used for most of the plots, and here I'm just specifying a histogram and I'm putting 2 variables at once, so I'm actually going to have 2 histograms. So we can look at the output. If you go online and look at the script, I've modified it slightly so that to show you how you can tweak the output. So the essence is the same. I'm requesting the same tables. I'm just trying to modify the way they are presented. So you see, I've bundled the tables together, and this is part of the SAS output. So I didn't copy paste to make it have this this particular alignment. So you see, the first table is the summary statistics. So intention on average is 8.26. With a minimum of 2, so and a maximum of 14. So the lowest and largest possible values have been reached. Some people have reacted very positively or negatively and are willing to buy the candies. Sex, of course, is a binary variable, so it's 0, 1. And we have about the same number of men and women, probably 1 woman more more than men, but more or less, one or two. Age next is around 30, so you see only adults participated in the study. Marital status, again, pretty balanced. Fixation time, note that some people looked at the ad for a very short period of time, and the maximum is 5.8 seconds. So that's very important in terms of modeling, because we'll see later how it can be dangerous if you don't take this fact into account. And emotion score, we said, it's a ratio of positive to negative probability. So probability of positive emotion to negative emotion. And so it's on average close to 1, but it's pretty spread out. Then you have revenue, classes, and frequency. So altogether, there's plenty of people in every group. And then intention, here you have the actual frequency for each of the outcome, but it's best to look directly at a histogram. Okay, so the largest class is at 7, and you could see this also probably at 7. You could see this, no, 8. So between 7 and 8. So this is a histogram. It's probably bundling them together. Whereas we could have used here a bar chart, would have been more adequate. But you can still see that nothing strikes out. There are some, the largest values and the smallest values seem to be not very populated, so pretty sparse records. And likewise, for the positive variables here, fixation and emotion, we see again that there's a few people who have very high score, but there's a handful at most. Okay, so there doesn't seem to be any outlier or strange value in our data. So one thing that's important to master for the continuation of the course is the terminology. So here the response variable is what we're interested in modeling, and in this case it's going to be intention to buy, whereas explanatories, sometimes also called covariates and machine learning predictors, are the variables we want to try to explain why with. Okay. So here it's not complicated. If intention to buy is the response, everything else are explanatories, including some variables that act as control. Okay, so we're interested in an effect of the fixation time and the emotion score, but we also want to adjust to make sure that differences that are due to these two variables are not because of difference in the repetition of sex, age, revenue, class, education, and marital status. So you need to somehow adjust for these socio-demographic variables to make sure that the effect you capture is truly not due to strong correlation between the explanatories that we're interested in. So let's have a look at some models. These models, of course, are not adequate as they are presented, but they will be used to simply illustrate somehow simpler models, and then we can take the parameter interpretation from there together during class. So here what I'm doing is creating first a scatter plot of intention and fixation. So I'm going to consider the model first with only fixation as covariate. So I'm specifying a scatter plot here, scatter, and then you have to specify the two coordinates, and I'm adding a regression line. So the third line here is the regression line, and I'm labeling the axes, and so then you run and you will get the scatter plot, which I'll show you in a second. The second block of code is the procedure for fitting linear models. So this is the first encounter we have with the GLM procedure. So you specify the data set as usual. And normally what you would have is just model. and we'll see that there are some other options we could pass on. For now, I'm only interested in the parameter estimates, so I'm actually going to use an ODS command to select the parameter estimate table. So there's a lot of things in the output that I'm not interested at the moment. And so that also means that some of the particular thing I should be requesting or asked to modify, I'm not going to do now. So ODS select parameter estimate, I found the name by using the trace. So if you've looked at the video, we have an example of how to use ODS trace on and trace off to see the name of the different tables, and this allows you to extract a particular one. So the syntax for our GLM, you specify the model. So on the left is your response, and on the right, separated by space, you put the explanatories. And normally we will add slash and then some other instructions such as SS3 when we'll be looking at tests. But for now, let's just consider this as it is, and then you will see that it prints a table of coefficient estimates and some tests that we will cover in the upcoming weeks. So this is the scatter plot. You could have repeated the same instruction for emotion, so intention as a function of emotion. So here we have the fixation time in seconds, and you can see there seem to be a positive correlation between fixation time and emotion. There's a lot of noise, so we do fit a line. The slope appears to be positive, the cloud seems to be positively associated, but points don't necessarily fall on the line very closely. We can also look at the parameter estimates. So this is the output table. The name of the parameter is in the first column, then you get the parameter estimates. So these are your beta hats. So here we have the intercept is 6.45. And fixation is about 1.14. Of course, these are estimated based on random data. So we have 120 observation, and you can see that they have uncertainty measure associated to them. So the standard error of the beta hat, its uncertainty, if you will, is here 0.42 for the intercept and 0.22. And the last two columns are tests that we will see next. So if I were to write down this model, the fitted model, so for y hat, basically you have beta naught hat plus beta 1 hat fixation, so that's 6.45 plus 1.14 times fixation. And so we're ready to interpret this. So, well, what is the intercept first? So 6.45, that would be the average intention in the sample. For person who did not fixate the ad. And that is impossible because we only consider people who fixated the ad. So some people looked at the ad for a very, very short period of time. So here it's plausible that the overall intention would be 645, but it's extrapolating beyond the range of the data. Okay. Next is fixation. So we're saying that if you're comparing two people, and here there are no other covariates, but basically if you fixate the advertisement for 1 extra second, on average the intention score increases by 1.14, and this regardless of the actual duration of fixation. And you can think that there could be caveats, so this model is not constrained. So it's the intercept is positive, so if you fixate the at 0 seconds, this is fine, and you cannot have negative time. But if you consider fixating the ad for say 10 seconds, then you will be beyond the range of plausible values. So ordinary least square estimates are not constrained, and so it is possible that the output is also implausible. So when we cover prediction, we'll see how we could address this particular fact, and when we get to likelihood models, we could also see how this could be incorporated. So this was a simple linear model with a continuous variable. Most of the explanatories we'll be using, though, are categorical variables. So how do we deal with them? Well, of course, we said before that a categorical variable is going to basically be defined, whether it's ordinal or nominal. We're always going to include it as a set of binary indicators. Now, if your categorical variable has a lot of levels, right, a lot of potential classes, categories, we're not really interested in doing and creating these by hand. It would be tedious in terms of programming, and so we'll be using the command class. So any variable that's categorical, including binary variables, you could define using class, and it will tell the software, even if this variable, if this column has numerical value, treat it as a categorical variable. And then you can specify which baseline category. So recall, if you have a model with k categories, we only put k-1 indicators, and the last one is mapped to the intercept. So you have to specify which one is referenced by the intercept. That's the baseline, and here you can specify. In SAS, by default, if you have a database and you go from top to bottom, so in the first line, the first value it encounters, that's going to be the reference. In R, there is no such thing as class, so just to tell you, the baseline is the first value in alphabetical or numerical order if you have a factor object. Okay, so if you fit the model in SAS and in R, you may have different output, but that's typically due to parameterization. So the model gives the same output, gives the same prediction, gives the same explanation, it's just parameterized differently. So let's just consider for now a very simple example to show this fact. So sex is coded 0, 1, so 0 for men, 1 for women. So it's a binary variable, it's a categorical variable. And I'm going to include it in the model as is. Okay, so that's what the first chunk of code is doing. I'm taking procglm, which is my procedure for fitting linear models. I'm selecting only in the output, I only want the parameter estimates, which I've shown you before. So that particular table. And here I'm modeling intention as a function of sex. So it is not meant to be a complete or adequate model. It's just to show you how it works. I could have used a slightly different syntax to get more or less the same output. And if I had sex equals men and women, so here you would basically, before declaring your model, you could put class. Okay, so that's where you would put define the categorical variable. Here I'm defining sex to be a categorical variable, and I'm saying my reference is men. If you wanted, you can try at home, change the reference, and see how it changes. And here I have the rest of the code. So a model intention as a function of sex. And here I've just placed, so normally we ask for the solution. To get the solution asks for, so here I'm not selecting the output. Solution asks to print the parameter estimates. And SS3 asks for particular parameterization, which we won't cover, but essentially anytime you fit a linear model, you want to have this option in. So let's compare the parameter estimates of the two different output. So your model here is beta naught plus beta 1 sex plus error, and the fitted model would be written as intention with a hat. Okay, these are the fitted model. Intercept, so it's going to be intention hat is 7.55 plus 1.36 times sex. So how do you interpret this? Well, as usual, when sex equals 0, that's men, you only have basically beta naught, so that's going to be the average of the baseline. So the average intention score of men in the sample is 7.55 points. Women have a higher intention to buy, so this is it's a contrast, so it's the average of women is beta naught plus beta 1. So here we have women which are at 8.91, more or less, as average intention. And so the difference between women and men is 1.37. So women have higher intention than men, 1.37 points higher. Okay, so you have here the interpretation, and you can check for yourself. Let's look at other categorical variables because it's not, the binary case illustrates the output, but it's pretty obvious. So as I said, if you want to include a factor or a categorical variable with k levels, so here they each have 3, we need 2 dummies. Okay, so I'm going to define 2 variables, let's say educ1 and educ2, and they're going to be equal to 1 if their respective value for education, so educ is 1, so educ1 is 1 for educ1 and it's 0 otherwise. So it's going to be 0 if, if educ2 or educ3. So if you look in the table at the bottom, okay, so educ1, 2, 3, you see the mapping. So if educ is 1, okay, so educ1 is 1 if education is 1, educ2 is 1 for education equals 2, and for educ3 you only get the intercept. And so you could read off the mean model. Basically what we'll get here is for education level 1, beta naught plus beta 1, for education level 2, beta naught plus beta 2, and for education level 3, beta naught. Okay, and we have 3 parameters. We're trying to estimate 3 means, so it makes sense if we have the intercept, we don't need a third binary variable. And if you notice this, if you added an extra column with 0, 0, 1, well, they would be collinear. Okay, so you can only have 3 of those, and because we typically want to keep the intercept, we leave it at there. So education 1, education 2, you could of course change the reference baseline if you wanted to have a different base category. So let's fit it 2 different ways. So here I'm going to create the dummies. So I'm going to create a binary variable. I'm creating a temporary data set called intention, which will be in the work library. So this is temporary. When you close this and you reopen, it's going to be gone. I'm going to copy statmod, and I'm going to create 2 new columns. One is education 1, which is a logical. If educ1, this is 1 and 0 otherwise. And the same for educ2. And then I'm just going to create this. And next I can run my model with this newly created data, select only the parameter estimates, and put the 2 dummies in addition. Right? So there's always intercept. If you wanted to get rid of the intercept, you'd have to add at the end of this line a slash and then no, I think it's no int or something to get rid of the intercept. But then you'd have to add a third binary variable. So we can look at this together. So the other way we could simply define class. So here I'm just going to define education using the class command, and I want to have the reference to be 3, and my model now is just intention as a function of education. And I could have foregone, I think, this reference equals 3. So you see now the parameter estimates. This is the output. So 7.11 is the average score for people in education class 3. People with lower education have actually higher scores. So something like 8.76 for people with lower education. So the average of education level 1 is the mean, is the sum of intercept plus education 1. So if educ1 is positive, that means that they have a higher value than the baseline. And so I'm just adding these 2 up. And likewise, intercept, so education 2 is also a higher intention to buy, and of the 3 categories, it is people with an education level of 1, so high school or lower, that have the highest intention to buy. There's considerable uncertainty here, of course. You can see that the variability seems to be significant, but bear in mind that they're also uncertain, they're random. So this is the output with the two binary variable edX1 and edX2. And if you look now at SAS output, the results are identical except that you have now an extra line which says education 3, and it doesn't have an estimate, and there's an extra column with B's, okay, the letter a capital B. So the results are identical, and I've already explained the interpretation, but I will show you in the next video what is this exactly representing. So we'll look at different linear parameterization. But based on the table, you could get the estimated means for each of the three groups. And as I said, the first group has the highest average. And what you get are, of course, contrast. So if you wanted to get the difference between education 1 and education 2, well, here it wouldn't be difficult. You can just subtract the average of 1 and the average of 2, or subtract the parameter beta 1 hat and beta 2 hat. But if you wanted to see how it's done, you can also refit the model by changing the reference category, and I'll leave you this exercise.